What's up guys, it's the Round Bottom Flask here, and welcome to our video lecture on stereochemistry. Now this is the part 2 of our video lecture series for stereochemistry, and in this case we will be talking about the rest of the topics that we have not discussed obviously in our first video. Now the RS configuration is something that is only on paper, and it's not actually observable. It's not actually observable in not only in nature but in a chemistry laboratory. And one way of distinguishing one stereoisomer from the other is through their optical activity. Now, stereoisomers, or rather chiral molecules, have the ability to rotate plane of polarized light. Now, when we say a plane of polarized light, now we can see that the light that a light from a light source actually radiates in every direction possible. Now, a plane of polarized light is a light that passes through a polarizer, wherein only light that passes through a single plane passes through a specific plane can go through that polarizer. Now, that line that light that passes through the same plane is what we call as the polarized light. Now, this ability of chiral molecules to rotate plane of polarized light is what we call as optical activity, and this is measured by a polarimeter. Now, a polarimeter has a light source, obviously. It has a polarizer, so it's similar to your polarized lens, wherein it only allows light at a certain plane, at a specific plane, to pass through. And when it passes through the sample, which is a solution of that chiral molecule, the chiral molecule will rotate that polarized light to a certain angle. And the amount of angle that is what they call this, or rather the degree of the rotation is measured by the analyzer, which is also just a polarimeter. The difference is that this one can be rotated, while this initial polarizer that filters the light in order to produce plain polarized light is actually fixed, while this one can be rotated, and the angle of rotation, or the degree of rotation that the sample will able to rotate plane of polarized light, is analyzed through here. So now this is actually an old style, or rather an old-fashioned polarimeter. Now, the automatic polarimeter will look like this. You just load your sample and it will automatically give you the optical activity. And that optical activity is expressed as your specific rotation, which is equal to, the observed rotation of a sample of a sample solution with concentration of 1 gram per ml, which enables to rotate plane of polarized light with a specific wavelength of 5 of this one here, and the path lengths or the sample container, or the path length of that sample container wherein the plane of polarized light was allowed to pass through the sample is 1 decimeter. So that's just the formula. So it's simply formulaic. You just key in your values. Now, the chiral molecules that can rotate plane of polarized light in a clockwise direction are called dextrorotatory, and those in opposite direction are levorotatory. Now, you have to remember that enantiomers will rotate, or rather enantiomers of the same molecule will rotate plane of polarized, will have the same specific rotation. However, they will just rotate the plane of polarized light at opposite directions. Now, there is also what we call as a racemic mixture. Now, a racemic mixture is actually a 1:1, or rather an equimolar mixture of the dextro and the leva enantiomer. Now, a racemic mixture will not exhibit optical activity since the optical rotation of the dextro and the leva isomer will cancel each other out, as you see in our illustration here. Next is we have diastereomers. Now, diastereomers are only exhibited by molecules that have more than one chirality center. So diastereomers are also stereoisomers, however, they are not enantiomers. So that means they are not mirror images of each other. Now, for example, here in the 2-amino-3-hydroxybutanoic acid, these molecules here, these stereoisomers here, are considered enantiomers because they are non-superimposable mirror images of themselves. However, this stereoisomer and this stereoisomer rather are not diastereomers because they are not mirror images of themselves. If you notice, they have a common configuration at the same chirality center. So they both have 2R. However, they differ in the third carbon atom, or in the second stereoisomer, the second chirality center, sorry about that, wherein the configuration is R, while here the configuration is S. Now, another type of stereoisomers is what we call as epimers, which only differ at one chirality center. So that means they will have the same configuration at all chirality centers, only except for one. We also have this unique type of stereoisomers, which is what we call as mezocompounds. Now, mezocompounds have chirality centers. However, they are optically inactive because it does not fit a criteria to a chiral molecule, which that it should not have a plane of symmetry. Now, mezocompounds, despite having chirality centers, still have a plane of symmetry. So let's have this mezzotartaric acid here. Now, if you notice, the mezzo-form of your tartaric acid has a chirality center at carbons 2 and 3 respectively. However, if you bisect this molecule along the CC bond here, you will notice that this part is identical to this part. So there is a plane of symmetry here. Another way of observing it is that when you rotate the molecule 180 degrees, it actually would look the same. Okay, the configuration would still remain the same. So another way of representing chirality centers is through Fischer projections here. Now, a Fischer projection is a 2D representation. It's just another two-dimensional representation of the three-dimensional aspect of the molecule. So let's have this molecule here with this arrangement, and we can see that the bonds. So what you just do is you just flatten this molecule, and it would look like this. Now the bonds above now obviously the center here, the vertex of the cross here will be your chirality center. Now the bonds above and below the chirality center are pointing at the back of the page, as you can see in this 3D representation here, while the side bonds are pointing at the front of, or rather are pointing at the front of the page. So So the analogy here, or the mnemonic that you can remember here, is the arms come out to hug you. So the arms obviously are at the side, so they are coming out to hug you. That means they are pointing forward. So this is an example here. So the same goes with molecules with more than one chirality center. It would look like this. You just flatten it out and this would be its Fischer projection. Now there are two properties of Fischer projection that are very useful, especially when you're trying to figure out its configuration. So Fischer projections will not change its configuration when you rotate 180 degrees. Okay, if you notice, if you rotate the 180 degrees, the arms on the molecules pointing forward, the substituents pointing forward is still at the sides, and the substituents pointing backward is still at the top and at the bottom. Nothing changes. You did not change the 3D orientation of the molecule. Then another is that if one group is held steady, the other group can be rotated without altering the projection's configuration. So it would, in the 3D structure, it would actually look like this. So this is your tetrahedral molecule. It would look like this. I hope you can see my illustration. Yep. Good thing it's visible. And you will see here that if you just hold one substituent steady, it's just doing a free bond rotation. You'll just move the others. You'll just rotate around this axis here without actually changing the 3D orientation of the molecule, and it will look like this. So C will now be at the front. Oops. So it would look like this. If you can see here, if we do a free bond rotation there, so if you just hold this steady, so you will just move the other three substituents. Now C will be at the front, B will be at the back, and D will now lie on the plane of paper. It's just that simple. So let's have this molecule here. Draw the Fischer projections for the following molecules. So this is a hydrogen group. This is a chlorine group, a chloro group, and this is a methyl group, and this is a carboxyl group. Okay, so what I can do here for letter A is, oops, why did I delete that one? So this is a COOH, this is a chloro group. So what I can do here is, so to make that look like the arms come out to hug you, I will flip the molecule 180 degrees. I will flip the molecule 180 degrees along to this direction, okay? So in order for it to look like this, so this will be your tetrahedral carbon. Your chloro group will now be at the bottom, since you will be moving, you will be flipping this carboxyl group going backward. So therefore the carboxyl group will be at the back, and the hydrogen group will now be jutting outward along with the methyl group. And therefore, when you convert that to Fischer projection, it would look like this. You just flatten it out, so it would look like this. So that will be its Fischer projection. So let's just do two examples, okay? So let's have letter B. So the same. So what I do is also I do a 180 degree flip so that it would look like this, wherein the hydrogen is pointing backward, but at the top of the tetrahedral carbon, your chloro group is at the bottom pointing backward. And your methyl group and your carboxyl group are coming out to hug you, as the mnemonic says. So when you convert that to Fischer projection, it would actually look like this. Oops. You just flatten this one out, so this will be its Fischer projection. Okay, and it will look like that. Okay, perfect. So that's it. So let's put our skills to the test, and let's try figuring out the Fischer projection based on the chirality center. Well, let's figure out, what they call this, the RS configuration, and just using the chirality centers, okay, or from the Fischer projections. So what is the configuration of the chiral centers in the following molecules? So in letter A, obviously, this will be priority number 4, this will be priority number 3, and between oxygen and nitrogen, oxygen is much heavier, so this will be priority number 1, and this will be priority number 2. Now, so I'll make this simpler for 1, 2, 3. Now, if you notice in the Fischer projection, for the lowest priority is at the side, that means it is pointing forward. And remember, in our Fischer assigning RS configuration, the lowest priority substituent should be at the back. So there are two ways to do that. The first thing, if you do it by the textbook, is actually we use the other property of Fischer projection, wherein we hold one of the substituents steady and we rotate the other 3. So we do that such that the lowest priority, or priority number 4, will be at the back. So I'll hold this one steady, then I'll rotate in a clockwise direction, so that your priority number 4 will be at the bottom, or at the back. So also the other substituents will also move along the arrows. So that would mean this will be the Fischer projection. 1, 4, 3 will transfer here at the side, and 2 will transfer here on the left. Okay. So then we trace the arrow from substituents 1 to 3, and we can see that the direction is counterclockwise direction. Therefore, the substituent is therefore the configuration is S. So this is S. Okay, my camera keeps moving. Sorry about that, guys. Yeah, I think it should stay that way. Yep. Next, another is the one that I taught you earlier, wherein we just figure out the configuration first before moving the force priority substituent at the back. So here, that is a clockwise direction. That will be R. If you flip the molecule, the R will become S. Therefore, the actual configuration will be S. Since we're flipping the molecule such that the lowest priority substituent is at the back. So before moving the lowest priority substituent at the back, the configuration is R, but after flipping such that the lowest priority substituent is at the back, the R will also flip into S. Therefore, the actual configuration of the molecule is S. Okay? Next is we have this one here. So obviously, they're both connected to carbon atoms. So obviously, hydrogen, So this one is CH2, CH3, and this is C double bond O, OH. This is C Br, and this is CO double bond O, Cl. Now, obviously, they already have a difference in bromine, and bromine is the heaviest among them. So therefore, this one will be given a higher priority. So this will be priority number 1. And if you notice, only the two, between the three, only one of them, only this one has a bond between a hydrogen atom. And since hydrogen is the lightest, this will be our lowest priority. So therefore, this will be our number 4. Now, between 2 and 3, which will have a higher priority? So they're already equivalent on this part because they have doubly bonded oxygen. Now, the difference is here. Now, since chlorine is heavier than oxygen, therefore, this will be given a higher priority. This will be priority number 2. This will be priority number 3. Now, we do the one that we do the trick that I've taught you earlier. We figure out the configuration before flipping, before moving the forced priority substituent at the back. So that is 1, 2, 3. This is a clockwise direction. That is R. When we flip our molecules such that the forced priority substituent is at the back, from R, it will become S. Therefore, the configuration is S. Okay, so let's focus on this chiral. Now, for letter C, we have 2 chiral centers. So let's focus on this chiral center here. Okay, now this chiral center has 4 different substituents. So obviously, this will be number 4. And since nitrogen is heavier than carbon, so this will be number 1. And this one will compete in the top 2 spot of the priority substituents. Okay? So this is carbon and this is carbon. So this carbon is C double bond O, OH. So that is also equivalent to C. It is equivalent to the C singly bonded to 2 other carbon atoms because of the C double bond O here, and we have OH. And this oxygen is also singly bonded to 2 other carbon atoms. Now in this case here, this carbon is bonded to oxygen, so they have a tie here, but this is bonded to carbon and this is bonded to oxygen. Now oxygen obviously is heavier than carbon, so therefore this will be given a higher priority. So this will be our number 2 and this will be our number 3. So we use the same trick. So before the flip, this is movement is R. When you flip it, since the lowest priority substituent is at the back, it's not at the back, so you flip the molecule to move it at the back. So the configuration will also flip. From R, it will become S. Therefore, the actual configuration of this chiral center is actually S. Another is that, now next is this chiral center. So obviously this will be our priority number 1, this is our priority number 2, and since this is bonded to 3 other hydrogen atoms, and it is bonded here to heavier atoms such as carbon and nitrogen, therefore this will be given a lower priority than this substituent, and this will be number 2, and this will be number 2, and this will be number 3. So we use the same trick. So 1, 2, 3. that is actually R. And since the priority number 4 is not at the back, we have to flip and after flipping, the R will become S. So therefore, this chiral center will also be S. Okay? Lastly, we have this molecule here. So let's have this chiral center. So obviously this is number 4, this is number 1. Between here and here, this will be given a lower priority. Since this is only bonded to carbon atoms, well, this one is bonded to carbon and nitrogen atoms, which is a higher, wherein nitrogen is given a higher priority in the Canning-Gould-Prelog system. Therefore, this will be given a higher priority. And this will be number 2, and this will be number 3. So we use the same trick. So 1, 2, 3. The movement is counterclockwise. So this is S. But since our lowest priority substituent is number 4, we have to move this at the back. And upon moving this at the back, the S will change into R. Okay, and the actual configuration will actually be R. So this chiral center will be R, and this chiral center, this is obviously number 4, and obviously this is number 1 since it is nitrogen, and obviously this will be numbers 2 and 3. The movement is counterclockwise again. So this will be S, and we flip the molecule. Since the lowest priority substituent is at the front instead of at the back, we flip it to move it at the back, and from S it will change into R, and the actual configuration of the chiral center will be R. So the technique here figure out the RS configuration of the molecule with more than one chiral center in a Fischer projection is that you consider each of the chiral center individually. Okay? Now, nitrogen-containing compounds actually, specifically amines, can also exhibit chirality wherein nitrogen will be at the center. Nitrogen will be the chirality center. And remember that nitrogen can only form 3 bonds, and the 2 non-bonding electrons will serve as your lone pairs, and that lone pair on the Lewis structure in the Lewis structure of amines in the nitrogen is considered as a substituent. And since a lone pair is significantly lighter than any other atom, thus it will automatically have the priority of 4. However, in theory that is possible, but in practice it cannot be observed because amines rapidly interconvert with each other in what we call as an amine inversion. So if we have an amine with 4 different substituents, which has a lone pair here, the lone pair actually shifts from this side to this side rapidly, and that cannot be isolated, and that is how amine interconversion occurs. It's similar to an umbrella being upturned by the wind, and then you're trying to bring it back to normal and being upturned again by the wind, and it's like an endless cycle. Now, but when you transform your amine into an ammonium salt, and it has 4 different alone it already has 3 different 3 different substituents. Since it already is an ammonium salt, the interconversion cannot occur, and thus your enantiomers can now be separated. So that's the end of my, so this is the end of my discussion for amines. I hope you learn a lot from it. And if you do, don't forget to subscribe to my YouTube channel for more chemistry lecture videos. Once again, this is the Round Bottom Flask. See you guys